Okay. That's what I want. Math 3339. So let's go a little bit to independent events again today. And let's work on a problem which is actually a typical and classical problem. Suppose that you have a system which consists of two switches. Here is switch number 1, and here is, actually those are two sensors. And sensor number 2. What you want is that they can be triggered with equal probability, or actually both sensors S1 and S2 can fail with the same probability. Now, if you have done a little bit of basic physics, this looks like a circuit, a very small circuit where you have two switches stuck in parallel to one another. So the electric current can come in and flow this way, or it can flow this way down. If one of the two trips the other, if the other is not tripped, it still allows the flow of the electric current. So what is the probability that we have a complete failure of the system? What is the probability that we have a complete failure of the system? Each one can fail with probability P.
Probability that S1 fails and that S2 fails.
So what is the probability that we're asking for? Probability of complete failure of the system, very correctly was identified by Martin, is the probability that S1 fails and S2 fails. So what is the probability of failure here? What can you say? How do we resolve the case when we have probability of event A and event B, concurrent occurrence? What do we do? What are our options? Can we multiply? Multiply what? Multiply them? What is the them? Okay, that is correct. Probability of failure of S1 times the probability of failure of S2. Can we multiply those probabilities? Yes, and why? Or no, and why? Why are they independent?
Because that's a conditional.
Oh, that's the header. It doesn't say that these two events are independent. That's the header over there. I had to put something to mark today's lecture. Okay? So that's the header.
Because
this is the way I put the two sensors. This is the way I connect them. Failure of S1 is independent of failure of S2 if I connect them this way. Otherwise, you cannot multiply the probabilities. Otherwise, you have to use the classical all-weather case, which is you use the conditional probability that one fails given that the other fails, times the probability that a specific one fails, which is the classical definition of conditional probability. Can I multiply probabilities here? Yes or no?
yes.
Why? What?
The chance of S1 happening.
Loud, please, everybody.
S1 happening isn't affected by the chance of S2 happening vice versa.
Why? Why is not? Why is that not? You're recycling the same answer.
Because if so, they wouldn't have the same
A is
probability.
equivalent to B because B is equivalent to A. That's what you're telling me.
Because if so, if their probabilities were dependent, then we would not have the same probability.
You are recycling the same answer. A is equivalent to B because B is equivalent to C, and therefore C is equivalent to A.
I'm not saying that they are independent because they don't depend on each other. I'm saying they don't depend
Why
on
don't
each
they
other
depend on
because
each
they don't-
other?
I'm saying they don't depend on each other because they do have the same probabilities, and if they can.
No, that's not. Yes, go.
The only dependency about them is the power coming into the thing. So if the power is not being there.
The power comes. The power always flows. Nothing. We say that nothing interrupts the power here.
You said that if one switch was off,
But we
Let me
don't
try
know
that.
that necessarily.
Let's hear. I mean, some guys had their. You had your answer. You had your chance. Let's leave the first chance to somebody else. Go ahead.
Yeah, the power continues, but like it can go both up and down, like just because the top one breaks.
Say it, everybody. Say it to everybody. The flow of the power can go up or it can go down. So if that fails, nothing stops the power from going down. Okay, so if that fails, this doesn't one have a reason to fail.
But couldn't that increase the chance that S2 fails because it's getting more power than it's supposed to?
Could, probably, and that's a valid view of that. But here we assume that even if that takes the entire load, it will not gonna trip.
But we don't have that information given. We need to have it.
Either you assume it and you say it specifically. Look, you can solve the problem either way. I'm not giving you an information. What is the probability, the conditional probability that S2 will fail given that S1 fails? I didn't give you that probability. I gave you the probabilities only that each one fails. So the only model you can use under the information that I gave you is the model of independence of failures. And you can say that I can assume that this one can still take the entire load that the circuit requires without failing. That actually guarantees independence. It's pretty much, so the probability of failure here is equal due to independence at that point, so independence of failure for the reasons we have explained. And even if it is not given in the problem, you can say it, you can assume it, and say it explicitly. I make that assumption. Why do I make that assumption? Because I want to do so. I cannot solve the problem otherwise with the information I'm given. Therefore, I'm going ahead and making that technical assumption. Is it a valid assumption? Yes, it is a valid assumption. That's the only thing you have to argue. I'm not arguing against making that assumption. I'm arguing that when you make that assumption, you have to support it with some argument. And the argument I made in the support of this assumption is that each of the two sensors can take the entire load without being overloaded and therefore having a reason to fail. It could have worked as if with just only one of them.
You can also say, since S1 and S2 have the same probability as it says right there, we can also just rewrite it as S1 squared.
Yeah, and that's what I'm going to do here. Probability of S1 fails times the probability that S2 fails. You see how I apply the independence? I turn the probability of an event A intersection B into the probability of A times the probability of B. That's what I applied. And this is equal to P squared. Well, a typical case like this, do you know where we have these kinds of typical cases? A case like this? Circuits, where else?
Rivers.
Hmm?
Rivers, the flow is redirected and you need to go from that gates.
So one floodgate is not going to open? Yes? Give me. Mm-hmm. Like? Can you imagine one?
Security system.
Hmm? The power breaker, if we put that for the power breaker, what do you want the power breaker to do? To cut the system off, okay? So if the power breaker is overloaded and this trips, and this doesn't trip, then you're gonna turn something into a Christmas tree. Where
Power
else?
to hospitals or other critical
Oh, power to
institutions.
hospitals, yes. That's a good way to do it, yes. Full availability systems, as we call
So
them.
you would generally have generators, which wouldn't have power.
Modern aircrafts, how many engines do modern aircrafts have? Two.
One, modern or model?
Modern aircrafts.
Four.
They have two. How many engines did they used to have 30 years ago? 30 years ago. Passenger aircrafts.
I wasn't born.
Hmm?
I wasn't born.
Yeah, but you've seen pictures.
One.
They have more
One.
engines than they need to invent.
Don't tell me that you that live in the time of visual information, you haven't seen how an aircraft looked 30 years ago.
Well, it depends on
Single
the engine
propeller.
capacity. There have been ones with 36
Don't
engines,
tell
and
me
there have
that.
been ones with one engine.
What?
There have been planes with one engine, there have been planes with 36 engines. There have
Passenger
been planes that needed
planes.
36
Passenger
engines.
planes. How many?
4, 2, 1, any of those.
They did four engine configurations. For what reason? One was you needed more power.
Fail safe.
The other was what?
Fail safe.
Fail-safe. Because planes could fly with one engine, so you was reducing the probability of failure of the system, instead with P, probability P to the fourth. Now that engines have become more reliable, you can put only two engines, and actually, I don't know if you have noticed that engines are now more close to the fuselage. The fact that the engines are more close to the fuselage is that if you lose one engine, then you have exactly aerodynamically the following effect. The effect that you probably have noticed if you paddle on a canoe kayak, if you paddle only one side, what do? You turn.
You just turn around in circles.
Okay, that's differential propulsion. And exactly the same happens if you have a plane with two engines and the left fails, you still have the right one, you can perfectly well fly, but you need to use a compensation with the rudder. Otherwise, you will start going into circles, and then you will go nowhere.
Then you'll run out of fuel, and then you'll crash, and then you'll die.
No, and actually you can even, if you have two engines and you lose your rudder, you can still, if your rudder doesn't work, you can still apply differential power and keep the plane straight.
So as long as you have
That
a
is
rudder or two
Martin.
engines, you are good.
Okay, so if you have when you lose your engines in the takeoff, that's where you have the biggest problem. Because you will not be able to have enough air lift.
Wouldn't
And-
SC be the best place for them to break? Because then they could be fixed without having to navigate with only two systems, one of which, if it fails, the plane will be unflyable.
Only when you're at full altitude. Full altitude where you have support enough lift. Okay, because there's that's also a difference. So this is the reason for which we do those parallel circuits. This is the full availability system. If I want to have a system that I want to secure something for breaking, for being burned, how would you put the two things together?
A certain,
Hmm?
definitely not. Definitely
If
not
I
in
want to,
series.
for example, if I want to have a very secure breaker, how would I do those two?
Definitely not in series.
Secure, right? Like
A
cars.
secure breaker.
Oh.
A breaker? Oh, you won't want breakers in series.
How would I line them up? Parallel?
One circuit 9, 1 9 and multiple breakers.
In a series, okay? I would do a serial connection. So if I do a serial connection, what is the probability of failure?
It would be the sum of the probability of each one failing.
P fails now system fails. When does the system fail?
When any of them fail, when A
If
or
both of them fail to break the system, okay? So if PS1 fails and S2 fails.
would it be or?
I think it's one. One's
And that's
on
what-
my
No, I mean fails to break the system. Think of them as breakers at your home. There is a power overload, and here you have high power, high current intensity that the system cannot sustain.
So S1.
And those are simple breakers, the ones that you have in your electric panel, okay? S1 and
does
S2.
not fail and S2 does not fail.
If both of them fail to trip, then you got something that will just go overload. If one of them fails to trip, but the other trips, you are safe.
So your
If
definition.
both trip, you're safe again. So let's say S1 fails to trip and S2 fails to trip. Yes, it is possible for both to trip.
Because if the first one breaks it, then the second one will get the current to break.
Yeah, but sometimes it's if they are very sensitive, they can both trip at the same time. Let's make that assumption.
I don't know what a break is.
What a breaker is?
It's a system meant to break.
I know what I pretend to get but you just said when you drew the picture, and
Mhm.
if one didn't work, then the whole system can work. That's what it looks like in the picture because I'm documentary.
Mhm.
If S1 doesn't work, how is S2 going to get the proper energy? How's the energy?
Let me put it in a different way. Suppose that you want to have a very secure system, so you put two metal detectors. Suppose that or you put two systems where you check people. Very careful. You put a metal detector and then the padding. Why do you do that? How would you, if you put them in parallel, then both work independently of one another. But if you force somebody to go first to the metal detector and then to the padding, then you have a better check. Correct? What is the probability that the system fails?
Mess.
If they don't go through one.
Let's think intuitively. Both have to fail, yes.
If they're independent, they should.
And they operate independently.
Yeah, they were operating independently. They have a higher chance of failure because you can pass through the metal detector.
Mhm.
You have to talk.
And then you pass through. So again, you got the same answer. Correct? What is the difference now?
I'm saying like you didn't pass after you passed through the metal detector.
Mhm.
And you wouldn't go. I thought that was what you were describing. You wouldn't. There's a independent one. There's not attacking afterwards. I'm saying that's the case. There's a greater chance.
Yeah, then how would you, and you can calculate this, so this is basically the independent failure, so it's P, it's again going to be P squared because of independence again. Now, what have changed between the two cases is not the fact only that I gave you this, the change in the connection of the two systems, the line-up of the two systems, but it's also I changed the phrasing. In the first case, it was a sensor that was allowing the flow. In the second case, where I put them serially, those are sensors which have to interrupt the flow if something goes wrong. That's why it's consistent to have P squared in both cases. If I want to interrupt the flow, then I line up my security systems, my security breakers, one after another. I put them as hurdles. You pass the first, you're nervous about the second. At least I'm going to catch you there. Yes?
In this case, you have the S1 in series with S2. The result is still P squared, same as in parallel. And
Yeah, but the statement is different. In the parallel, I wanted to allow the flow. Here, I want to break the flow. That's why I use the example with the breakers. Although you don't typically put two breakers at your home, because typically the first one will break, and the second one will not probably be as likely to fail. Sometimes we do, though. When you have, in modern houses, we put two breakers. For example, you have these, you've seen the bathroom outlets that have the push button, the test button.
Yeah.
Those have a breaker inside. And this is a breaker which comes after a breaker. The main breaker is in the panel, but this is a local one. And they are serially arranged. Why do you do that? Because you want to have full availability, full protection, to have a better protection. Typically, the one in the bathroom should fail first, the one in the outlet, and then the other should fail. Or the other may not even have the chance to fail.
It also would protect it.
And they're slightly different. I'm sitting a little bit because technically they're different. One is thermal, where the other is also detecting the possible electrocution. It detects the differential between the neutral and the phase. I used to love, actually I worked a little bit in my life as an electrician. So in Europe, and when I came over here, many things had changed, and also the safety requirements had changed, because as I discovered easily, 110 is really hard to kill. You have to be very skinny to be killed, and very lightweight to be skinned by 110. It gives you a shock. You can't imagine what is 220, which we use in Europe. It really gives you a big shock. All right, and now let's go to, again, back to do some problems with conditional probability, which is, we did some problems with independence, and we did, now I want to mix several things. And by the way, there are some cases, there are some things that I want to talk about because they're very, very useful. And let me see if I can find them here. Image analysis. All right. Oops. What is this thing doing? Okay, I can't find it. Yeah, this is. Okay, very important cases of conditional probabilities that I want to talk about. Here we have, let's say, a condition, which is we have a property, an attribute, and we have a test, a mechanism, a device that can tell us whether the property is present or not. Now, think of it as a medical test, like the HIV test. The HIV test tells you, okay, I probably detect something that looks like HIV antibodies, but it's not a confirmatory test. You need another test, a so-called screening test. So the fact that the test comes out positive does not necessarily imply that the condition is present. It's like your house alarm. Many times the house alarm trips. And it trips and says, oh, there is some burglar inside. Something is moving inside the house. It's nothing else but your kitty cat moving very close to the sensor and triggering the sensor. That's the sensor said, okay, there is somebody, I detect movement. But the movement is not exactly the movement that you expected, the movement that can be harmful to you. The burglar inside the home collecting items. It's just the kitty cat that decided to leave the couch and move to the litter box, possibly. Okay? So that's what we have. And in this case, we can have the following configurations. We can have the true positive, which in computer language we call a hit. And that true positive is something that is very important because it's telling us, hey, the condition truly exists. It's a true detection. We can have a false positive. The condition doesn't exist. That's why I have C bar. But still, you got a hit. You got an alarm. That's the case with a kitty cat. It's not a burglar, but it's a kitty cat. Then you have the false negative. Well, the burglar is inside, but the sensor doesn't go off for some reason. There's no trigger. That's bad. You come back and you find your house empty. And then there's also the true negative where the sensor remains idle because there is no movement inside the room. Or there is movement that is not harmful. And that's the true negative. Now, in the medical testing, it's very important to understand how we call this. The probability of getting a true hit is called sensitivity of the test. Let me put it in another way. You get the HIV test and the test comes out positive. What are you going to do? Kill yourself? Well, in the older times, don't laugh. In the older times, it was really, really bad to have a positive test because there was no medication. Essentially, that was a death sentence. Worse than a death sentence. Because if you get a death sentence, you can appeal. And you can still live many years until you appeal, until all your appeals can go through. Before any medication existed, it wasn't like that with HIV. So that to have a sensitive test, a test that has high probability of a true hit, to have the condition and to truly have the condition and get a detection, was very important. Yet those tests were not very sensitive when they were first released. The other is the false alarm rate. Well, it can drive you crazy, but it's not going to kill you to have a positive test. You do further tests and you find out. So it's the false alarm rate, the second one. Then there is a third one, which tells you the ability of the test to clear those who don't have the condition. Say, you're fine. And that's called specificity of the test. And an important concept, and you understand why it's important, is the so-called receiver operating characteristic, which is essentially a plot, a curve, that can be derived if on the horizontal axis we put the false alarm rate, and for a given false alarm rate, for each given false alarm rate, we calculate the sensitivity of the system. That is done by using gold standards, situations that we know exactly what is happening and we benchmark against those situations the performance of the system. Now, what do we know? We know that if you turn the false alarm rate to 0, then the probability of having true hits will also drop, actually will go down to 0. Once you start moving the probability of the false alarm rate to 0, from 0 to something positive, even minuscule. Sometimes we use 10 to the negative 3 or 10 to the negative 4. So small numbers. Theoretically, the probability of the true hit should go to 1. So here we have the ideal receiver operating characteristic curve is 0 here at the 0, 0 point, and immediately as we jump to positive probabilities, even very small ones, that hit should go to 1 and stay up to 1 all the time. So it has this jump. That's the ideal receiver operating characteristic curve, the one that you see. That doesn't happen in practice. So a very good receiver operating characteristic curve will look like this. Let me point it with my, it will go like that. Asymptotically it will be close to 1 when you have higher false alarm rates. If the false alarm rate is equal to 1, that should go to equal to 1. That's it. If it's not 1 there, then the system is utterly bad. And the system is not good if the receiver operating characteristic, instead of being over the diagonal, it's below the diagonal. Okay? Now, that receiver operating characteristic curve shows how good a system is, how well the system performs, and how robust the system is in detecting whatever you need to detect. And the better the system, the more close this curve is going to be to the ideal. So if you really want to compare two systems that aim in detecting or designed to detect the same condition, the one that gives you the better receiver operating characteristic is the better system. So this is a way to compare unequivalent, non-equivalent systems, essentially. Systems that are designed to do the same thing, but are not exactly the same. How are you going to compare? How are you going to say one is better than the other? Well, that's a common way to benchmark performance of these systems. Okay, now of course, the other thing I want to talk at this point is the so-called detection. So let me go to my previous one. Are there any questions about this? Because now I'm going to use it. I'm going to derive Bayes' rule, which is very important. Then we'll do some application about Bayes' rules. So here is Bayes' rule. Actually, I will derive it. So we did the test. Here's the problem. We did the test, and the test came out positive. What is the probability that you have the condition? That probability is called positive predictive value of the test. And see how I have reversed the conditions. The heat is T given C. Now I have C given T, which means which means the event to have the condition given that I have a positive test result. And that's exactly what you're interested in diagnosing. That's the diagnostic value of the test. If the HIV test comes out positive, what is the probability that the individual has the condition? That's the puzzling question. Now, see that the fact that what you have here is also called posterior probability. Because it's a probability that occurs, that relates to an event that has occurred after something else has occurred. Now you know a little bit of information here. You know that the test came out positive. So that is what has occurred in the meanwhile. And therefore the probability C given T that the condition exists given that the test came out positive is a posterior probability because it follows the event of the test. We want to calculate this. So to calculate this, we simply apply the rules of probability. T and C given the probability of T. That's exactly the definition of conditional probability. And now here, I'll leave some space because actually I'm going to write one more equation, P of T. What is P, T, and C? Here I use the definition of conditional probability, so that will be T given C times the probability of C. Do you remember that from the rule of, from the definition of conditional probability? And if you don't, just believe me, take my word for that. You can review it in the video last class, the previous class. And now I want to calculate this. By the way, the probability of C, the probability that someone has the condition, in the medical language is called prevalence. So this is the prevalence of the condition here. And it's something that we know. We do statistics. So we know it. Without knowing it, there is no way to calculate that posterior probability. So what is the probability of T? That's the puzzling question. Well, let's draw a little bit here, a picture. Well, here is all people, the square, and that is divided in two categories. Left is C, and on the right is C bar. So on the left, I have the people who do have the condition, and on the right, I have the people who do not have the condition. And you understand that C and C bar are two disjoint events, are exclusive events. You can't have and not have the condition at the same time. Is that clear? Now, when you test, inside, let's say T is to have a positive test, is to be inside, pictorially, inside this set, and outside of this is T bar. You tested negative. What is T equal to? Well, T has two parts. One part is this one I mark with the red, and the other is what remains. So T, as you can see, can be written as the union of T and C, T and C bar. So that thing with words says that if you test positive, two things happen. Either you test positive and you have the condition, or you test positive and you don't have the condition. These are the only two situations that can occur. And these two are exclusive events. This one is the red here. And therefore I can add their probabilities. So the probability of T is the sum of these two probabilities. Now let's take those two probabilities separately. The first one has already appeared. Is this conditional times the probability of C. So here I have the sensitivity, and here I have the prevalence. And if you see that one, it's actually the numerator. To calculate the posterior probability I spoke about in Bayes' rule, I just simply need to calculate this. That's the only thing I don't know. And I'm working to calculate it. Likewise, we do this. And if you want to see what is the probability of C bar, what is T given C bar? How did we call this? T given C bar? No, how did I call notationally T given C bar? It's a false positive, okay? That's a false positive or a false alarm. So what is this here? This is the false alarm rate. FAR. What is P of C bar? This is 1 minus the prevalence. And what is the false alarm rate? Well, we mentioned it before. The false alarm rate, PT given C bar, is equal to 1 minus PT bar given C bar. What is this one? This is the specificity of the test. And these are numbers, sensitivities, specificities, and prevalence are numbers we get from statistics. Namely, the specificity and the sensitivity come from the manufacturer of the test, and the prevalence comes from general epidemiological studies in the context of medical conditions. So now we have everything. Let's put everything together. So, this one, and that's Bayes' rule. And I will keep it like this because it's easy to memorize it. That's Bayes' formula. Now, the denominator essentially is the following: is P of T is equal to this. And that's another interesting formula which is called total probability law. So that's the total probability law. Here this is Bayes' rule. And I told you how to compute this and this, the false alarm rate and the prevalence. We get them from specificity, and of course, this one from the prevalence. Any questions? So let's do an example. So let's take an HIV example, the Aura Quick. Have you heard of it?
No.
It's a swab. We take a swab from the mouth, under the tongue, and I think it takes about 5 minutes, 5 or 10 minutes. It gives you a chromatographic reaction. And that can tell you whether you test positive or you test negative. Okay, now this Aura Quick, according to the manufacturer, has a sensitivity which is 99% and a specificity, so this is sensitivity, which is 98%. Given that the HIV prevalence in the general population is 3%, what is the probability that you have an HIV infection if you test positive? What do we do to solve the problem? Well, we use Bayes' rule. So we have to use the rule I have here. And to do that, That's the probability we need to use. What do we use here? 0.99 times 0.03. Those are the easy terms. What is the next term that we need to put? We need to put this one that I have here times the 1 minus the prevalence. So that term here, as we mentioned, this one, is 1 minus the specificity. So this one will be 1 minus 0.98. And the other term is 1 minus 0.03. So what's the probability now? What do you think the probability is? Roughly, can you give me a ball figure? Can you eyeball it? Mm-hmm. Look at these numbers here. This appears in numerator and the denominator as well, okay? I'm going to lift it a little bit so you can all see it. This one is like this. 0.97 times 0.02, the other 0.99 times 0.03, they're approximately the same. So this number is approximately 50%.
That's not very good.
That's not very good. Can I give you an easy test, 50%, with 50% chance of predicting correctly?
Yes.
Flip a coin. Why does it come so low? Okay, let's do something else. If we change the prevalence, we put the prevalence to 10%. Now the numbers will come vastly different. If you put the prevalence to 10%, then these numbers change. So this will become 0.1, 0.1. This is again the same, but this is 0.9 here. And if you work the numbers now, you will see that there is a difference in this new case. It goes higher. And the reason is that we changed the prevalence. If the prevalence is higher, the positive predictive value becomes high. The positive predictive value became small, 50%, pretty much equal to that of flipping a coin, because the prevalence was very small. So it's very hard, very rare to find the condition. Actually, 10% is a true percentage in a group of in a population group. Actually, there are two population groups that have 10% prevalence of HIV.
Almost one.
Did you do the calculation?
No.
What is? 85%. Thank you. So it goes up to 85. It's an almost certain event, okay? Almost.
What's the meaning of prevalence of HIV? Like the amount of population?
When we say prevalence of HIV is basically the percentage of people who have HIV infection, or the probability that you pick one from a specific group to have